Okay, let me start by reminding you a few basic notions which we studied last time. So first, there was notion of homotopy between continuous maps between two topological spaces. We can consider a pair of maps F and G from X to Y, and yes,
Yeah.
I think I did. Thanks. So there was a notion of homotopy between two maps, F and G, so morally it means that there is one parameter family of functions labeled by an element of a unit interval, so that at the beginning of interval I have F, and at the end of interval I have G. So that is a function F from X times interval to Y, such that F restricted to 0 is F restricted to 1 is G. And second important notion which we considered was a homotopy equivalence between topological spaces X and Y. And by definition, it was a statement about existence of a pair of maps acting between X and Y in opposite directions, so that their compositions are homotopic to identities. In particular, there was a let me clarify that it's from the definition it immediately follows that if X and Y are homomorphic, so for homomorphic spaces we will use this the notation, this double, this sub equality with tilde, homomorphic. If two spaces are homomorphic, they are necessarily homotopic. And this immediately follows from definition, because for homomorphic, the definition of homomorphism is that the existence of a pair of maps like this, continuous maps like that, between X and Y, so their compositions are just identities. But of course, we know that the identity is of course homotopic to itself. So if they're homomorphic, they're necessarily homotopic. Okay, and so we ended by formulating the following proposition, which will provide, as a result of this proposition, will provide us with many examples of homotopy equivalence. And the propositions was the following. If there exists deformation in tract of X onto subspace A, then X is homotopy equivalent to it's this subspace. We'll control it as follows. So by definition, of, so let me remind you the deformation of retract. So by definition, there should exist function f from x times the interval. Is a homotopy between maps from x to itself, such that if we're restricted to 0 here, I have identity on x, and we're restricted to the end of the interval. It's a composition of an embedding map of subspace A and a retract R. So we have the following commutative diagram. So we have x, so this defines the map from x to x, which is obtained by composition of a retract R to A, and an inclusion map IA. And by retract, by definition, the continuous map to the subspace such that if restricted to A, it becomes identity. So in particular, so R is a retract. From the definition, it follows that, by definition, from the definition follows that the restriction to A is the same as identity on A, but this statement can be reformulated such that if I compose R, so R is a map from X to A, that composed map with inclusion, so this will become map from A to A, is the same as identity. Okay? And from the existence of this homotopy, it follows, so since it's a homotopy between identity on X and this composition, it follows that the composition of those two maps in a different order is also homotopic to identity. Now on X. And then by definition, so of course this is, we know that identity on A is homotopic to itself, so this means by definition that these two spaces are homotopically equivalent. Questions? Yes, the question? Sorry. So we are close to defining the notion of fundamental group, but before doing that, we want to introduce, we want to study the properties of paths, what is called paths in topological spaces. So you probably already had a definition of the notion of paths in topological space. For example, this appears in the definition of path connectedness. But for completeness, let me define it again. So a path in topological space X is a continuous map. So again, I'm kind of being redundant here, so I already told you that by default all maps are continuous. Of course, it's a map from an interval to X such that well, not such that, and this is not a condition, but just a statement that the part of the definition, so this is the definition of paths, and the second part of the definition is that this, the values of 0 and 1 are called endpoints. More precisely, this is a start endpoint, and this is beginning and ending endpoint. So of course you can visualize this. So this is a map from an interval, some topological space X, and the image is indeed looks like a path between x0 and x1. And we can always specify the direction. It starts at x0, starts at x0, ends at x1 as a vary argument from 0. Okay, so next we want to consider operations on paths. The first operation which we want is inverse. So let f, we take f be a path. Then pass from x0 to x1. Then f bar is a new path, which is called inverse. The new path defined by the following formula. The bar of S is the same as and of course now it's a path from x1 to x0. Another operation is composition of paths. So this is different from composition of functions. So it's defined as follows. So let fg be a pair of paths. Then this is so let me generate by f. Let me. So here we actually need a condition such that the g of 1 is coincides with f of 0. Then we can define the composition of paths denoted by f dot g is a path, is a new path defined such that the value of this function of s is defined as follows. So this is the same as the value of g of 2s when s varies from 0 to 1/2, and f of 2s minus 1 when s varies from 1/2 to 1. So you can see that this is indeed, this formula gives me a continuous function because if I plug here s1/2, here I have a g of 1, and here at the end of this interval I have f of 0. So there's no jump, this is a continuous function. And so you can, so this operation can be visualized as follows. So for example, in particular, the first operation, so if you have a if you have a path f, the original path f looks like that, then the path, the inverse path is essentially the same path, but you go in opposite directions, because it's just given by the following definition of the argument. And now we can, so what about the composition of paths? So I need to take another path, say G, and it should be such that the end of G coincides with the start point of F. So it should look something like this. You pass G, and so the composition of G and F is a path which looks like this. And so essentially, when my argument is in the first half of my interval, I go along G, and when it's in the second half of the interval, I go along F. So if one can understand it's the gluing of two paths. This is it. And to do this explicitly, I need to rescale. So I need to rescale my original function f was defined on an interval, and the g was defined on a unit interval. The composition, I can understand composition as just taking f and g and rescaling the argument. So from 0 to 1/2 I have f, and from 1/2 to 1 I put values of g. Okay, any questions?
Are the notation f bar and f dot g universal?
Kind of. Yeah. Well, yeah, I think this is most common. In particular, in the book of Hatcher, he did the same notations. So next we want to define the notion of path homotopy. Path homotopy between pair of paths f, g, so we need to consider a pair of paths which has the same endpoints. You have the same start point and the same end. So this is considered fixed, and the path homotopy is a map from an interval interval to x such that it satisfies the following condition. So first you want f of s0 to be the same as value of path f, f of s1 to be the same as the g of s. So this so far this is looks essentially the same as the definition of just an ordinary homotopy that we have before, homotopy between a pair of functions f and g. But we want to add additional conditions which will distinguish this path homotopy, the notion of path homotopy from the notion of ordinary homotopy. So we want the condition that f of 0 t is x0 for any t, and f of 1 t is the same as x1. So how can we understand this? So the function f is defined on a square. So let me do it like this. 1, 0. And so you map it to x, and so you want, so if it's so the first condition means that so if my actually let me choose it. It's going to be better later. Yeah, let me choose it like this. So for example, the first condition means that this part, so if I restrict, you can see the values, restriction of my big F on this edge, so this takes the same value as my path F. This edge is mapped to the image of path F. And similarly, this edge is mapped to the image of path G. So we know that the endpoints of G and F are the same. That's why I do it like this. And moreover, so these two conditions mean that all those h is mapped to just one single point here, and the whole right edge is also mapped to a single point here. So again, similarly to the usual homotopy, you have one parameter family of maps, but you require that they always this family of, you have a family of paths which is fixed for which endpoints remain fixed. So usually we will be so by default when we're talking about homotopy of paths, this means it's considered as a path homotopy. But I will try to specify to my experience that you can say path homotopy, not ordinary. And okay, let's see. Yeah, in the case of the usual homotopy, we have the following statement: path homotopy is an equivalence relation on the space on the set of all pass X is fixed endpoints.
No, but path homotopy is a homotopy, right?
Is a particular example, yeah, is a homotopy.
So there's nothing to prove except that every path homotopy, every path is a path homotopy to itself, which is okay. I mean, there's nothing.
Well, I mean, if two paths are if you're considering this on the same yeah, I'm not going to prove. I was just wanted to say that this is similar, completely analogous to.
But this is a corollary of the last one.
Well, if you're considering this as a path homotopy on this set of paths with fixed. Well, the point there may be a situation when they exist. In principle, they can exist a homotopy between paths which is not path homotopy. So one should be careful because I mean you may start with some paths you can move around also moving, changing your endpoints, and then you come back.
Yeah, so it is kind of similar, but not really a corollary.
No.
Oh.
But what I want to say is that the proof is completely analogous. You just consider it immediately. So no. But essentially, you just repeat all the arguments. So, okay, now we want to prove some properties of this path homotopy. So yeah, if two paths are homotopic, so for path homotopy, yeah, we kind of use we will use the same notation as for path homotopy and ordinary homotopy. But again, by default, if you're considering paths, we mean path homotopy. And yeah, this first means if two paths are homotopic, the inverses are also homotopic. And second property is that if you consider a pair of pairwise, four pairwise homotopic paths, then the compositions are homotopic. then the third property is some sort of associativity for compositions between paths. And for associativity, so if it's only associativity up to homotopy, so it's not actually true that those compositions in these different orders are the same, but it's true up to homotopy. And the fourth property is that the composition of paths with inverse is homotopic to something I will denote by C with index x0. So this is a constant, so this is by definition is a constant path staying at x0, which is the same as n1, 0. So by definition, it's just for any s, it's the value of this function is the same as x for any s.
Why C they are not equal? And C, the associativity. No, point C.
It's not true, right? So as we will see, this is not true. It's not equal.
Is there a simple
So-
example?
Yes, because
No, but-
one is from 0 to half and the other one is half to 1. And the place of the t where the t place is different.
The graph is the same, but the velocity.
Yeah, so the
Well, we will see. I will write it. When I prove, we'll see explicitly that it's not. We will need to some not real. So that's why important. So we couldn't consider just something like to define a group associated a manifold. Naively, okay, you can consider do this composition of paths and just define the group of paths. But this wouldn't work because your associativity will fail. So, but you need to, if you consider them up to homotopy, then you will have associativity, and then you can define some group structure. So this is, in a sense, this is important that this is only homotopy. Okay, so let's prove first. The first thing, so suppose this is given by the homotopy is derived as a function f, and then we want to show that from this it follows that the inverses are also homotopic, and the homotopy is realized by some function f bar, and indeed we can just take this function f bar to be defined by the following formula, the same as f 1 minus s t. So this is a continuous function from a square to my topological space X, and indeed it satisfies all properties required for path homotopy. So let me make it explicit. So, for example, if I take it the second argument to be 0, this is the same as f1 minus s of 0. This is the same f1 minus s. This is the same as f bar of s. So it's a homotopy starting from f bar. And similarly, this will be the same by similar manipulation. This will be the same as f prime bar of s. And another condition we want to check is the value when the first argument is 0. So this is f of 1t, which is f of 1, which is the same as f bar of 0. This is indeed what we want, and similarly f bar of 1t is the same as f bar of 1. So these are properties which, by definition, we need to realize homotopy from f bar to f bar. The second property was the composition. Okay, so again, suppose there exists some homotopy f between f and f prime, and there exists some homotopy G between G and G prime. Then we want to show that there exists some homotopy, let's say H, between their compositions. Sure. And so one can present an example of such homotopy by giving an explicit formula in terms of known f and g, known homotopies f and g. So this is defines the function when s from 0 to 1/2, and this defines my function when s is from 1/2 to 1. And, so one can check that it's easy to check that this is indeed continuous. There is no continuous function. It's the same because the values of this g and f are the same when s is equal to 1/2, because we remember that the start of f should coincide with the end of g, and the same for f prime and g prime. One can also argue this just better in the following picture. So the h is a function from a square to x, and it will look like this. So first, if you restrict it to the bottom edge, this restriction is given by the composition of functions f and g, and we know that the composition is built by just rescaling the argument by multiplying by 2 and putting these functions together like that. And similarly, at the top edge, we will have a composition of functions g and f prime. And so to construct the h, which is a function on the square, we do similarly just combine the functions f and g, which is defined on the square, by rescaling one of the arguments. So g was sorry, this was the wrong. so this was G here. Yeah, it's a composition of G and F. So first we start with G and then we have F. And so here is the image looks something like this. So if you have there was a G and then plus F, and G was there was homotopy between G and G prime. So this is the image of this square of this rectangle, and there was a homotopy between F and F prime like this. And all those vertical edges, again, they are just marked to single points. This is how the structure of my map H. Third property is this associativity after homotopy. So suppose you want to find some homotopy K which realizes this. And so before doing this, let me write explicitly what is the compositions on the left and right hand side in terms of the original functions f, g, and h. So this composition, so the value of s given by the following formulas is h of 2s is half, and then it's g 4s minus 2. That will be f of 4s minus a. And this is for s from 3/4 to 1. And, so this is obtained by just explicit use of the definition of the composition. And this composition in this order is given by the following function: h of 4s g x minus 1 f s minus 1. This is when s is 0 to 1/4. This is when s is from 1/4 to 1/2. And this is when s from 1/2 to 1. So you can see from this explicit formulas, this is not this is a different, generally different functions, unless there's something like constant. But already, if I take this, for example, linear maps to like linear paths to R itself, I take my x to be R, and this will be just a linear path. This will be already a different functions. And so I will write an explicit formula for the homotopy K, but let me first visualize. I mean, how do you want to construct it geometrically? So again, let me draw out this square on which our homotopy will be defined. And so at the bottom we have so let me actually let me construct homotopy from this to this. Well, it doesn't matter, but let me construct homotopy from this to this. So at the bottom, I will have this function, and it will look like this. So from 1/2 to 1, we put a scaled function f. From 0 to 1/4, we put a scaled function h. And from 1/4 to 1/2, we put a scaled function g. But on the top, from 0 to 1/2, we put a scaled h. And here, so here we first compose g and f. So we're going to scale them first by 1/2 and then another time by 1/2. So the f g is scaled by multiple of 4 and by 4, and this f is scaled by 4. With the argument of scale. And we can realize homotopy by doing the following. So we can, as we vary t, our parameter in the family, we change the scale in h so that its domain of definition is scales from 1/4 to 1/2, and similarly we will scale the domain of f from 1/2 to 1/4 here. And more explicitly, you can write it like this. The result, the explicit function, the explicit formula for the homotopy as follows. This essentially realizes explicitly what I said in words in this picture. So you can check by yourself that this is indeed does the job of doing those rescalings. And this is indeed continuous function which realizes homotopy between those two paths. Questions? So the final property is that I want to check that this is homotopic to a constant path. So let me present some homotopy G which realizes this. First, so what is this composition? I'll write it explicitly like this. This is, you can also express using the original function f, which is 2, 1 is s. GA, the homotopy to be the following. So let me, so in a moment I will explain what does this mean. More dramatically. But you can explicitly check, also you can explicitly check later yourself, as this is indeed realize this homotopy. Again, this is a function defined on a unit square, so that at the bottom I want to have a composition of f and f bar, which is essentially the same as f with inverted argument. And so what I want to do, and at the bottom I want to have a path which just stays at x0. Constant path which stays here. And what I can do is by so this is so the path in the logical space X pass. I have something like I start at x0, I have pass f, and then I have f bar which goes in the opposite direction. So what I want to do, I want to continue, so this gives me a composition. If I go first like this and then like this, what I want to do is I want to continuously deform it to a path which stays at x0. So what I can do is kind of move, start to deforming this endpoint to x0. And more precisely, this means that, so if I'm in this triangle, I just, the function defined on this, along the lines, along the horizontal lines will be just restriction of this function f to this subinterval here. And the same here, but when I'm here in this in the other triangle, and I go around along the horizontal lines, I have a constant functions. So this gives me a family which starts at this composition of f and bar and ends with a constant path. So all three edges here, they are mapped to a single point. Okay, so this was the last property. Questions?
X0 is f of 0?
Yes, x of 0 is it was in the formulation of the proposition, which is the same as 1. So now we're finally ready to define the fundamental group. Fundamental group of a logical space X to define, I need to take some additional data, which will be what is called a base point. Just any point in X is a group which is defined as follows. So it's a group which is denoted by pi1. So it depends on X, logical space, and a choice of a point in X, X0. So as a set it defined as follows. So this is a we consider set of all maps from an interval to X with such that f of 0 is the same as f of 1 and the same as my base point. Consider this up to path homology. So this is a space space of paths both base points coincided with my base point in X, quotient with respect to path homotopy equivalence relation, and with group structure given by composition paths. So as usual, by square brackets, I denote an equivalence class with respect to chosen equivalence relation, which is path homotopy. So in words, one can say this here. Group is a group of path homotopy classes of loops. So by loops, so loop is by definition is a path whose endpoints are the same. Both endpoints are the same. So it's a path which starts and ends at the same points. So this defines it, so this quotient, this equivalence relation defines as a set, but we want to equip it with the group structure. We want to say how the elements of the set, so how the equivalence classes, what is the group structure? So what is the group product of a pair of elements? And we define it like this. So this defines me a map from pi1 times pi1 to pi1. Of course, there are some things which need to be checked here. So this is we need to check that it's actually like a self-consistent definition. So first we need to check that this is actually well defined. So here we define it by choosing some, we define this the product by choosing some particular, taking some particular representatives in my equivalence classes. We need to check that this is independent on the choice of representative. The product is well defined. For example, in particular, let me take another representative f prime of the same class. So take f prime to be path homotopic to f, and take g prime to be path homotopic to g. And let me calculate what this formula gives. For this pair, so the classes, the equivalence classes are the same. So we expect to get the same answer by using this formula. So this is so by definition this should be the composition of paths. The equivalence class is the composition of paths, but we know that since using one of our properties that we showed before, we know that for a pair of this follows from one of the properties which we prove. So the class of the composition will be the same as the class of the composition of the original pair f and g, and this is the same. It's the same as a product of equivalence classes of f and g. Indeed, we have a well-defined notion of operation from pi1 times pi1 to pi1. But we also need to check that this, this gives me a well-defined map like this, but we also need to check that this map satisfies group axioms. So first we want there should exist identity element. And for identity we take a class of a constant map staying at x0 at my base point. So indeed, for identity we need to check that if you multiply it from left or right or any other group element, it gives me the same group element. So in particular, if I multiply it from the left on some group element given by a class equivalence class of a path f, so this is the same by definition of the product is the same as the composition of a constant pass and pass F, but of course this is a the same. So since we know it's obvious that the composition of a constant pass with pass F is homotopic to F itself, right? So again, we trivial to construct homotopy, so we have a pass F. At the bottom here, we have a composition of F and a constant map, and sorry, whatever. So we just consider homotopy that we rescale as we changed our parameter. We just rescale my functions as functions. Scale argument s, so that in a linear way everything here is mapped just to 0. Okay, and similarly, if you multiply from the right, this is the same as the original. Second is existence of inverse. So for any element f, there exists inverse, and this falls from the fact that as an inverse we can take a class of a pass of an inverse pass. So we have to check that this is both left and right inverse, but let me just do it for left inverse. So I need to check that this is gives me identity, which I introduced here, and so by definition this is the equivalence pass equivalence class of the composition F with F inverse, and indeed. So we showed that this is homotopic to a constant pass, and its class is identity in the fundamental. And finally, we want to check associativity. Take this product in this order of 3 elements, in this order. So we know that this is the same. So by definition, this is so I replace this by class of a composition of parts, and then we do the same way. So here we're just using the definition of a product structure, and here we use the property which we showed in the proposition just a few minutes ago. So we use the fact that this is homotopic to a composition made in a different order. So the classes, the equivalence classes are the same. And this is again by using the definition of the product structure. So this gives me associativity. Questions?
Can be non-abelian?
Yes. Actually, it can be anything you want.
Any?
Yes.
You mean that for any group you can found topological space
Yes.
for which can prove?
Also infinite group.
Well, I mean, there is explicit you can explicitly construct this topological space.
For any group.
Yes.
Or
This is what called classifying space.
so we start from the group and then we define the topological space.
Yes.
But it's like easy or it needs very advanced stuff.
Well, there is explicit construction, which is, I mean, that does require many techniques. But I mean, it's kind of complicated construction, but it doesn't require too much additional knowledge. I mean, it's easier to construct it if you. I mean, it's easier to define it if you're familiar with knowledge of cell complex.
Yeah.
If you're familiar with the notion of cell complex or something like CW complex, then it's a natural construction in this kind of setting. Yeah, I'm not sure if you have time. I mean, maybe we will discuss this later. Because it's, I mean, this construction it requires some time to, and I'm not sure if you have it. Okay, so so we saw that by definition we need to define this fundamental group. We need to introduce some additional information, additional structure. We need to choose a base point. But the following proposition tells us that the dependence on the base point is actually quite. I mean, in a simple case, it's.
Connect?
Hmm?
Connect?
Yeah, so the proposition is the following. So for a path connected topological space X, the fundamental group defined for base point X0 is isomorphic to the fundamental group defined for base point X1 for any pair of points in X, which means it follows that so in this case can talk about, and this is all you can find in the literature, talk about just fundamental group of X itself. So you're gonna meet this base point data, but if you do it like this, we have to remember that we talk about, we consider this group is given us up to isomorphism. We don't have a particular realization of this group, it's just some group which we consider up to isomorphism. But in a sense, as we know in the algebra, in a sense, we want to say that the isomorphic groups are the same. In a sense, are the same groups. Okay, so the proof of this proposition goes as follows. So X is path connected, and it follows by definition there exists a path such that which starts for any pair x0 and x1, there exists a path which starts at x0 and ends at x1. And then let me using this path, I want to define the following map. So move the map from pi1 maybe careful here, so I define it from each b. This is map from pi1 of x1 pi1 x0. So just if I take some element here represented by loop f starting and ending at x1, it is mapped to the following composition of class. So this is well defined because, let me see, so I have here x0 and x1, so I have some loop f starting and ending at x1, and I have a path h going like this and a path h bar going like this. So if I take a composition H, F, H bar, this gives me a path starting and ending at x0. This is well defined. So first I want to check that this is not just a map between sets. This is actually a homomorphism between two groups. So we need to check that it respects group structure. So indeed, if I take so let me take a product of elements here on the left. This is by definition this is the same. So what I want to check is the product of elements here is mapped to a product of group elements here in this pi1. So I take this product. So first I can rewrite it like this using the definition of the product in the fundamental group, and then so the result of my map here is the following. By definition, this is the following composition. So as we learned, if I consider equivalence classes, it doesn't matter. The order of this composition doesn't matter, so I can forget about brackets. because up to homotopy, all possible ordering of compositions are the same. And then I can use the fact that the composition of H and H bar is homotopic to a constant map, and I can always insert it, as we saw, I can always insert the composition with the constant map is homotopic to original map, so I can do manipulation like this, and so then here, so far I just use the properties of compositions, so properties of the homotopy between paths, and now I use the definition of the product between group elements here. Is H bar F H times plus over here, and which is what we want. This is another way I can write this is the value of beta H on class of F times beta H of class of F. So this proves that this map is indeed homomorphism, so it respects the group structure. And it has another property is that it has inverse beta H bar, which is also homomorphic. And so how do we check it? So inverse. So if I take my if I use if I instead of H I use inverse of H, this of course by the same formula defines me a map from here in the opposite direction. And so let me check that this is indeed inverse. So to do that, let me consider composition, the value of the composition of two maps, for example, in this order. And the composition, the check for that this is inverse in a different, the right inverse, so the left inverse will be similar. So now I use it, so let me first use the definition of beta H bar. So the same definition here, just change H to H bar. So this would be this. So I changed H, swapped H and H bar, and then I apply beta H to this. So I use this formula. And then I use the fact that we know that these guys, the composition of those guys, are homotopic to constant maps, to constant paths. And this is the same stuff. So this is indeed inverse. And so we know that if I have homomorphism which has an left and right inverse, then it's which is also homomorphism, then it's isomorphism. Questions? show that this is so the fundamental group, which can understand the next fundamental group, so which is a group in a sense a group of loops starting on the zero, doesn't depend, or cross connected at zero, doesn't depend on the form. But in order to is there any pair of fundamental groups for a pair of base point isomorphic, but let me point out there is no in general there is no canonical isomorphism. So the isomorphism may depend on how exactly you choose your class H, which connects these 2 points. So these groups are isomorphic, but not canonically isomorphic.
What does mean isomorphic but not canonically?
Well, there is no. You cannot take a choice. I mean, you cannot give a prescription of what isomorphism. There is no distinguished choice of isomorphism. There can be different isomorphisms. There is no distinguished choice of isomorphism.
And can it have another isomorphism apart from the one that we just defined?
Yeah, you can take other paths. So you can take H.
No, I mean a different.
You can take some paths and credit paths.
No, I mean without such path.
Hmm?
I mean something else. I mean up to some path and can it have or
if there is so in principle, I think there could be the question in principle, a priori there could be isomorphism which is not realized by paths. I mean, you can take kind of, just this some group which is not defined as a fundamental group of the space, but still isomorphic to this group.
But if we have any isomorphism, we can find the bus to define it in this way. To say that the isomorphism can be written in the way we wrote the isomorphism before. So, right?
Well, not necessarily. For example, in general there can be isomorphism, which is not realized by this beta H. At least. I guess I don't see a reason why it should be possible to realize this as a pass. Yeah, for example, if you we'll consider it's hard to talk about examples so far because you haven't had that for if you have S1, the fundamental group will be Z. Has a and you can consider, well, as an additive group, and you can consider, for example, isomorphism, which changes the sign, but it's not realized by pass. It's not realized by change of base point.
If we take a group, right, and we take beta H, right? If we take the automorphism group of the group, right? If we say that because the set of this beta H is itself a group, right? Because
Yes.
if we compose,
Well, you can write all inner automorphisms. You
Yeah,
can inner automorphisms you can realize.
I thought that what I wanted to say.
But they can be outer automorphisms.
Yeah, that's what I said. So we can, for such example, where the group of automorphism is not like that. No, I mean that. No, it's not. It's not that. I mean, if the group of the beta H is isomorphic to the group itself, to the fundamental group itself. Because it's in
Well-
correspondence. Because if we take two different classes, two different H's, the isomorphism are different, right?
No, but no, it's not. I mean, the group of inner. It's not. Sorry, what do you want to? Okay. I mean, it's a very special case that the group of inner automorphisms is the same as the same.
What?
I mean, it's a very special case when the group of possible isomorphisms related by this beta H is the same as pi 1 itself. I mean, you have an action of pi 1 on pi 1. This is indeed the case. This is given by conjugation, which gives you an inner automorphism.
Yes. So what he asked about if always the group of automorphism of the fundamental group is the inner group. It's not his question.
If group of
He said if all isomorphisms are equal, is conjugation.
no, but we know that this is not true, right?
What?
We know that it's not true. That not
Yes. But if it was true, then this is a statement.
Yes.
You can say it like
If
that.
it's as I said, all inner automorphisms you can realize.
Yes. So if we want to see an example, we just choose a space where the fundamental group don't satisfy this. His group of automorphism is not. Yes.
Yeah, for example, Z.
Yes.
Okay, so just before to make a point before we last point before we end is that the following definition: pass connected X is simply connected. If pi 1 is 1, I mean it's a trivial group. So if you encounter this notion of being simply connected, so one way to define it is just to say it's a from block. Okay, let me stop here.